So we are at the data link layer whose role is frame by frame delivery. As part of this, it provides many services. In this video, I will provide an overview of one such service, error control. The details will follow in other videos. Now, what is error control? Errors are nothing but altered bits. For example, if the transmitter were to send a 1, the receiver incorrectly decodes it as a 0 and vice versa. Error control refers to detecting such errors as well as recovering from such errors. Now, what do you think causes errors? We have covered this before. Errors are caused due to distortion of signals due to frequency dependent attenuation or noise. We covered all this as part of the physical layer. There are two types of errors: single bit random errors and bursty errors. Suppose if this were the transmitted sequence, in single bit random errors, each bit is in error with a certain probability, let's say 10 to the power of minus 5. So at the receiver, I'm just assuming this bit is in error and rest are all fine. So this is what you're going to receive. In bursty errors, a bunch of bits that are adjacent to each other will be in error. So in this case, what the receiver will see could be something like this. So this bunch of bits are in error. So this is the case of a bursty error. I think you will relate to this better through this example. Suppose you have a noise spike that lasts for 1 microsecond, and let's assume that this noise spike causes errors in the data stream. Suppose the data rate is 1 Mbps. How many bits do you think will be in error? So 1 Mbps boils down to 1 microsecond bit duration. If you assume that this noise spike overlaps this bit duration exactly, then this is going to produce single bit errors. Now suppose the data rate is 100 Mbps. How many bits will be in error now? That's right, this is going to produce a burst error of 100 bits. Errors are a reality. You can't escape them. Now, should we bother detecting them? Data fidelity is a very important concern. In other words, you want your data to reach the other end intact. Suppose you are an e-commerce company and you send this statement as part of the email, and let's say due to errors, the P became T. Now, this is something which you would not want to happen, right? So it's important to detect errors. So apart from data fidelity, is there any other reason why you want to detect errors? Another reason to detect errors is to prevent wastage of resources. What do I mean by this? Suppose you have a packet that has to travel many hops to reach the destination. Now, if this packet suffers an error in the very first hop, there is really no point in transmitting over many hops and wasting the bandwidth at all these intermediate links because it is anyway in error. So it's useful to detect errors, and let's say because of this, we put in mechanisms in place to detect errors. Now, what do you do after detecting errors? You could just drop the frame. What are you seeing? How can that be okay? Ethernet does just that. When error rates are small, you could delegate the responsibility of recovery from errors to some higher layer protocols like TCP, which will recover the losses, so it's not your headache anymore. Or in certain cases, like in the audio applications, a few losses don't hurt the application. In other words, you cannot really make out that anything went wrong. Even if something went wrong, you can rely on the human protocol there to recover the errors. Basically, the person can say, can you repeat that please? I couldn't follow what you said. Something like that. On the other hand, if you think that it is important to recover the frame because the loss rates are high, you could employ two mechanisms. One is called error correction, where the frame itself carries enough information that you can correct the errors. The other is retransmission, where you detect the error but you cannot really correct it, in which case the receiver signals the sender that it has seen an error, and then the sender is going to retransmit the frame. This I'm calling it as retransmission. So here are a few things about error correction and retransmissions. In error correction, typically requires a lot more bits to be sent as part of the frame than error detection. In other words, both error correction and error detection need some bits to be sent as part of the frame to do the correction or detection, but correction typically requires more bits. And another point to note is that these redundancy bits are sent all the time. In other words, every frame carries these redundancy bits. On the other hand, the retransmission requires another copy to be sent only on error. In other words, you don't retransmit unless there is an error in the frame. So given this, if the losses are extremely rare, which of these mechanisms would you employ? Error correction or retransmission? Retransmissions, right? Why send all these redundant bits all the time, these extra redundant bits needed for error correction all the time when errors are so rare? You might as well recover from that rare errors by asking the sender to send the copy again. So error correction is useful typically when the error rate is very high, in which case you don't want to retransmit each and every copy. It's good to send the redundant bits so that you can kind of recover it. It is also useful when the cost of retransmission, by here cost, I mean, for example, the latency of retransmission is too high. This can happen in a satellite link. You don't want to wait for a really long time for the copy to come. So you might as well send some error correction bits so that you can recover the error. And error detection is naturally useful for the opposite scenarios. That is when the error rate is low and the cost of retransmission is not high.